Today we're going to be talking about vapor pressure. But before we talk about vapor pressure, we need to talk about evaporation. There are 4 things that you need to know about evaporation to understand vapor pressure. Evaporation, as you already know, is the process of changing from a liquid to a gas. And because molecules are in constant motion, some of those molecules will always have enough energy to escape the attractive forces that hold the liquid together. Although we usually think of evaporation happening when it's warm, evaporation actually occurs at any temperature. Rain puddles outside on a sunny day will evaporate faster, but they still evaporate even if it's cloudy or cold. And the last thing is that evaporation only takes place at the surface of the liquid. Only the molecules that are at the top have the opportunity to escape to the gas phase. Let's look at a picture. This picture represents a glass of water. All of the molecules in this picture, both the liquid molecules and the gas molecules, are in constant motion. At any given temperature, some of those liquid molecules have enough energy to evaporate. Remember that the gas phase has more energy than the liquid phase, so only the highest energy molecules can escape the forces that hold the liquid molecules together. Remember from before, those were hydrogen bonds. Only the molecules at the surface of this glass of water have the opportunity to evaporate if they have a high enough energy. Only these molecules at the surface can escape to the gas phase. These molecules underneath are blocked by the ones above them. So evaporation only occurs at the surface of the liquid, but it does occur at any temperature. Now that we understand evaporation, we need to take a time out to talk about some terminology. It's important that we understand when we should use the word vapor as opposed to the word gas. We use the word gas to describe any substance that is usually found in the gaseous state. Can you think of some examples? Maybe carbon dioxide, or hydrogen, or oxygen. All of those things are normally gases, and so that's what we call them. On the other hand, a vapor is something that is usually a solid or a liquid, but at that time is found in the gas phase. For example, we say water vapor when we're talking about steam because water is usually a liquid, but sometimes it can be a gas. It would sound a little funny to use the word water gas. So instead we say water vapor. We have one more concept to talk about before we get to vapor pressure, and that is the idea of a dynamic equilibrium. So let's think about what those words mean. How does a person sound who is a very dynamic speaker? They might use several tones of voice. They might walk around while they speak. Dynamic, in other words, means motion. Dynamic is a word that means in motion. So how about the second part of that term? Equilibrium. What does it sound like? It sounds like the word equal. And there are 4 conditions that have to be met to have a system at equilibrium. Number 1, the rate of evaporation must be equal to the rate of condensation. every molecule that evaporates has to have a matching molecule that condenses. If one molecule leaves the liquid, one molecule must enter the liquid. These are the things that are equal at equilibrium. The second thing that must be true to have a system in equilibrium is that the macroscopic properties are constant. Think about what that means. What is microscopic? Something that is very small that you need help to see. Macroscopic is the opposite. Things that you can see or measure with just your senses. The macroscopic properties are constant. The things that you can see or measure, like temperature or visible changes or things that you can hear, must be the same. In other words, there must not be any of those changes. The third thing is that you have to have a closed system. In this case, that means a lid. We're eventually going to get to talk about vapor pressure. Vapors are gases. If you don't have a lid, you can't observe them. So you have to have a closed system. And the fourth thing that you need to have equilibrium is saturated air with vapor. That means that the air above the liquid in your container is full of the vapor you are looking at. Remember last year in Earth Science, we talked about relative humidity and how when the humidity is 100%, the air is holding as much water as it can. This is the same idea. The air above the liquid in your closed container is full of as much vapor as it can hold. All right, now we've done all of our groundwork. It's time to actually get to the point of this lesson, which is, what is vapor pressure? Vapor pressure is the pressure caused by the vapor above a liquid in a sealed container of equilibrium. Let's look at a picture. First, we need a container. And then, our container needs a lid. And some liquid. The vapor pressure is the pressure caused by the vapor that's above a liquid in a sealed container of equilibrium. And equilibrium means that for every molecule that evaporates, one molecule has to condense. So inside this sealed container, we have a dynamic equilibrium. Every time one molecule evaporates, one condenses. And the vapor pressure is the pressure that's caused by the liquid up here. There are two things that vapor pressure depends on. In other words, there are two things that can make vapor pressure change. The first thing that vapor pressure depends on is temperature. As the temperature increases, the rate of evaporation increases. This makes sense. Rain puddles outside will evaporate faster when the temperature is warm. So as temperature goes up, evaporation goes up. If you have more molecules in the vapor phase, then you'll have more pressure. This is because as you increase the temperature, you are increasing the kinetic energy of the molecules. So as the molecule's energy goes up, more of them will have enough to break free of the forces that hold the liquid together. So more molecules have enough energy to escape. That means evaporation goes up. More evaporated molecules means the vapor pressure goes up. The second thing that affects vapor pressure are the attractive forces of the liquid itself. Some liquids are held together more strongly than others. Think about the difference between water and maple syrup. Which one do you think would evaporate faster? Water. It's not held together as strongly. Maple syrup would have stronger intermolecular forces. If it has stronger forces holding the molecules side by side, there will be less evaporation, and that means less vapor pressure. This is because, with stronger forces, not as many molecules will have enough energy to break free. Now that we understand what vapor pressure is, we can learn about a couple of interesting applications of it. The first one has to do with boiling. Boiling occurs when two things happen. The first is when the vapor pressure of a liquid becomes equal to the atmospheric pressure that is on it. The vapor pressure is the pressure of the gas above the liquid in a sealed container. You can change the vapor pressure by changing the temperature or changing the liquid itself. When the vapor pressure equals the atmospheric pressure, boiling will begin to occur. The second thing that happens when boiling occurs is that the liquid that is not at the surface of the container starts to become a gas. Remember, we talked about evaporation only occurs at the surface. Boiling occurs throughout the depth of the liquid. Remember from before that the boiling point is the temperature at which a liquid boils at a certain pressure. Now we can take that definition a little further and say that the boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. Remember from before that the normal boiling point, or NBP, is the boiling point when the surrounding pressure is 1 atmosphere. When you are at standard pressure, your boiling point is called the normal boiling point. And now that we know when boiling occurs, we can begin to learn about how boiling occurs. Boiling occurs when the vapor pressure is equal to the atmospheric pressure. So how can we get that to happen? Let's look at an example. Here's an example. The vapor pressure of water is equal to 0.022 atmospheres at room temperature. 0.022 is less than 1 atmosphere, which is our standard atmospheric pressure. So how can we get the vapor pressure of water to change so that it will be equal to atmospheric pressure? Here is our vapor pressure down at 0.022 atmospheres. And here is our standard pressure up at 1 atmosphere. How can we get the vapor pressure to change so that those two things are equal? In other words, what change will make the vapor pressure go up? Remember that we said vapor pressure depends on temperature. When the temperature goes up, the vapor pressure goes up. So if you want to make the vapor pressure of water equal to atmospheric pressure, in other words, if you want to make the water boil, heat the water. When you heat the water, you are increasing its temperature. Increasing the temperature raises the vapor pressure until it reaches atmospheric pressure. And when the two are equal, the water boils. But why does the vapor pressure have to equal the atmospheric pressure in order to boil the liquid? It has to do with the pressure being created inside the liquid and the atmospheric pressure that is on the outside of the liquid. In this picture, the yellow arrows represent the atmospheric pressure, and the green arrows represent the vapor pressure of the liquid. In the bottom of the container, the black circle represents a bubble beginning to form as the liquid starts to boil. The pressure inside the bubble from the gas that is inside the bubble is caused by the vapor pressure of that substance. Outside that bubble, there is atmospheric pressure pushing inward. If those two forces are not at least equal, the outside pressure, the yellow arrows, will be stronger, and the bubble will collapse. When the pressures are equal, or the inside pressure is greater, then the bubbles can form and hold their shape, and the liquid boils. So why do those two pressures have to be equal to boil a liquid? So the boiling bubbles don't collapse. If the pressures aren't equal, the bubbles can't hold their shape. When those two pressures are equal, the bubbles form and the liquid boils. Remember from Earth Science last year that the air pressure in different locations on our planet is different. Standard pressure, being 1 atmosphere, is taken at sea level on the shoreline of the ocean. Not every place on Earth is at sea level. So how does the different air pressure affect the vapor pressure, which affects the boiling point? Which of these two places, Pikes Peak, Colorado, or Galva, Illinois, has less atmospheric pressure? Pikes Peak. Because the elevation is higher, there's less atmosphere above it, so Pikes Peak has less than 1 atmosphere of pressure. So what does that do to the boiling point? Remember that the vapor pressure of water is 0.022 atmospheres, and that in order to make water boil, you have to make the vapor pressure equal to atmospheric pressure. So let's think about how does the atmospheric pressure of some of these places compare with ours in Illinois. Illinois is not quite sea level, but it's pretty close. So we'll treat that as standard pressure at 1 atm. Remember from Earth Science that air pressure goes down as elevation goes up. So the place on our planet with the lowest atmospheric pressure would be the place with the highest elevation. That's Mount Everest. So Mount Everest would have the smallest difference between its atmospheric pressure and water's vapor pressure. Although Pikes Peak in Colorado is no Mount Everest, its elevation is still pretty high for the United States. So the difference between the atmospheric pressure in Pikes Peak and the vapor pressure of water would be a smaller difference than the one for Illinois' standard pressure and the vapor pressure of water. known as the Mile High City, Denver's elevation would still be higher than ours in Illinois, which would make its atmospheric pressure still lower than ours in Illinois. Here is Illinois at about 1 atmosphere of pressure, and the difference between our atmospheric pressure and the vapor pressure of water is larger than the difference between any of our 3 other locations and the vapor pressure of water. Last, we'll include one example that's below sea level. If you traveled down into a mine, the atmospheric pressure would still increase, so it would be higher than the one in Illinois. So next, let's think about how these differing atmospheric pressures would affect the boiling point. We know that water boils right around 100 degrees Celsius here in Illinois. So how would that boiling point change if we traveled to Mount Everest? The difference between Mount Everest's air pressure and water's vapor pressure is smaller. So how does that change the amount of heat needed to raise the vapor pressure up to atmospheric pressure? If the difference between atmospheric pressure and vapor pressure is less, it will take less heat to raise the vapor pressure to equal atmospheric pressure to make the water boil. So if you tried to boil water on the top of Mount Everest, it would only need to get as warm as 70 degrees C. Water at the top of Pikes Peak would boil at 89 degrees C. And water in Denver, Colorado boils at about 94 degrees C. And if you were trying to boil water in a mine, it would reach 107 degrees C before it boiled. So how does that difference in boiling point affect the way our food cooks? If you boil water in Denver, is that going to cook your food faster than in Illinois? Here's your pot of spaghetti, ready for dinner. You put it in the water, and the water boils at 94 degrees C. So what is it that cooks your food? Is it the bubbles in the water, or is it the heat? So the answer to our question is that foods actually take longer to cook in Denver because the boiling point is lower, the water is cooler, and it's the heat that cooks your food, not the bubbles. So the cooking takes longer.